My dear students, welcome back to our channel. In this video, I will be explaining the BSc third semester subject Chemistry as prescribed by Osmania University and other universities of Telangana. We will go through the important questions and answers one by one. Let's begin with a quick revision. Unit 1 first important short question is: explain the anomalous behavior of post-lanthanides. Answer: anomalous behavior of post-lanthanides. The post-lanthanides, elements after lanthanum, like Ce2Lu, show anomalous behavior because their 4f orbitals are filled gradually, and these orbitals are poorly shielded from the nucleus by 5s and 5p electrons. As a result, the nuclear charge increases, pulling the electrons closer. This causes a steady decrease in size across the series, known as lanthanide contraction. Because of this contraction, some lanthanides and post-lanthanides show unexpected, anomalous properties. For example, zirconium Zr and hafnium Hf have almost the same atomic size, even though they are in different periods. Their chemical properties also become similar, making separation difficult. In simple words, the anomalous behavior happens due to poor shielding of 4f electrons, leading to small sizes and similar properties among elements that should have been different. Trick to remember: poor shielding, more pull, small size, similar guys. Next important short question is: write briefly about solvent extraction method for the separation of lanthanides. Answer: solvent extraction method for separation of lanthanides. The lanthanides are very similar in their chemical properties, so separating them is quite difficult. One useful method is the solvent extraction method, which uses organic solvents to separate them based on how well each element dissolves. In this process, a solution of lanthanide ions is mixed with an organic solvent, like tributyl phosphate or kerosene, and a complexing agent such as HNO, nitric acid. Each lanthanide forms a slightly different complex compound with the solvent. Some complexes dissolve better in the organic layer, while others stay in the water layer. By repeating the extraction several times, the lanthanides can be separated one by one. Example: separation of Ce superscript 3 and La superscript 3. Cerium forms a more stable nitrate complex and moves faster into the organic solvent than lanthanum. Easy tip to remember: different love for solvent, different movement, easy separation. Next important short question is: 3. Discuss the uses of lanthanides and their compounds. Answer: uses of lanthanides and their compounds. The lanthanides are very useful metals because of their unique magnetic, optical, and catalytic properties. Even though they look similar, each has special uses in daily life and industries. 1. In alloys. Lanthanum and cerium are used to make strong and heat-resistant alloys. For example, mish metal, a mixture of lanthanides, is used in lighter flames. 2. In electronics and TV screens. Lanthanide oxides like EO, europium oxide, and TBO, terbium oxide, are used in color TV tubes and LED screens to give bright red and green colors. 3. In glass and polishing. Cerium oxide is used to polish glass and also to make special camera and telescope lenses. 4. In nuclear reactors. Some lanthanides like samarium are used to absorb neutrons in nuclear reactors. Easy tip: light, lens, lighter, and reactor, lanthanides make life brighter. Next important short question is: 4. Explain the differences between lanthanides and actinides. Answer: differences between lanthanides and actinides. The lanthanides and actinides are both F-block elements, but they show some clear differences because their electrons fill different orbitals. Property lanthanides actinides. Orbitals filled 4f orbitals 5f orbitals. Atomic numbers 57 to 71, La to Lu, 89 to 103, Ac to Lr. Radioactivity mostly non-radioactive, all are radioactive. Oxidation states mostly +3 show variable oxidation states, +3 to +6. Occurrence mostly natural, many are synthetic, man-made. Complex formation weak tendency strong tendency due to higher charge and size. Example, cerium, Ce, is a lanthanide with +3 oxidation state, while uranium, U, is an actinide with +3, +4, +5, +6 states. Easy tip to remember. Lanthanides, calm and natural, actinides, active and nuclear. Next important short question is 5. Write the preparation and structure of Ni-Co. 4. Answer. Preparation and structure of Ni-Co. Nickel carbonyl, Ni-Co, is a volatile, toxic liquid and a famous metal carbonyl discovered by L. Monde. It is widely used to purify nickel. 1. Preparation, Monde's process. Impure nickel reacts with carbon monoxide, Co, at 50-60 degrees C to form nickel carbonyl. Ni, impure, +4 Co Ni, Co, _4 gas. This volatile Ni, Co, is then decomposed at 200 degrees Celsius to obtain pure nickel. Ni, Co, _4 Ni, pure, +4 Co. 2. Structure. Shape, tetrahedral. Oxidation state of Ni, 0. Bonding, each Co donates a lone pair to Ni, sigma bond, and receives back pi electrons, pi back bonding. Electron count, Ni has 10 d electrons plus 8 electrons from 4 Co 18 electrons, obeying the 18 electron rule. Easy way to remember. Ni plus Co tetrahedral magic heat gives pure Ni, 18 electrons make it stable. Next unit 1. Long questions. First important long questions is: discuss the causes and consequences of lanthanide contraction. Answer: causes and consequences of lanthanide contraction. Lanthanide contraction is the gradual decrease in the size of lanthanide elements from La to Lu despite having increasing atomic numbers. This is an important concept in F-block chemistry because it affects the chemistry of later elements in the periodic table. 1. Causes of lanthanide contraction. 1. Poor shielding by 4f electrons. In lanthanides, electrons are added to the 4f orbitals, which are deep inside the atom. The 4f orbitals poorly shield the increasing nuclear charge from the nucleus. As a result, the effective nuclear charge, Z_EFF, experienced by the outer electrons increases, pulling them closer to the nucleus. 2. Steady increase in nuclear charge. Each successive element has one extra proton in the nucleus. Because 4f electrons do not shield effectively, the electron cloud contracts, reducing atomic and ionic sizes. 3. Cumulative effect. This contraction occurs across the series from La Lu, making the later lanthanides smaller in size than expected. 2. Consequences of lanthanide contraction. 1. Similarities between 4d and 5d elements. Elements in the 5th and 6th periods, like ZrHF, N-beta, have almost the same size, even though HF is in the 6th period. This makes their chemical properties very similar, complicating separation. 2. Effect on ionic radii. The contraction reduces ionic radii, affecting the stability of complexes and the strength of bonding with ligands. 3. Effect on melting and boiling points. Smaller atomic size increases density, melting point, and hardness for later lanthanides. 4. Influence on chemistry of post-lanthanides and actinides. Lanthanide contraction helps explain the anomalous behavior of post-lanthanides and similarities with actinides. Example: zirconium Zr and hafnium HF have almost the same atomic size, 160 pm, due to lanthanide contraction, even though HF is 1 period below Zr. Both form similar oxides and chlorides. Easy tip to remember: poor shielding plus more protons, smaller size, similar chemistry later on. This rule is key for understanding F-block chemistry, separation techniques, and periodic trends. Next important long question is: to explain the postulates and limitations of Werner's theory of coordination compounds. Answer: postulates and limitations of Werner's theory of coordination compounds. Werner's theory was proposed by Alfred Werner in 1893 to explain the structure and bonding of coordination compounds. It was the first successful theory to describe the arrangement of ligands around metal ions. 1. Postulates of Werner's theory. 1. Primary and secondary valency. Metals have two types of valencies. Primary valency corresponds to the oxidation state, satisfied by ionic bonds, usually with anions. Secondary valency corresponds to the coordination number, satisfied by covalent bonds with ligands. 2. Coordination number. The number of ligands directly attached to the metal defines its secondary valency. Example: in Co-NH-Cl, cobalt has primary valency 3, bonded to Cl, and secondary valency 6, bonded to 6 NH ligands. 3. Fixed geometric arrangement. Ligands are arranged regularly in space around the metal ion, octahedral, tetrahedral, or square planar. 4. Nature of bonding. Secondary valency involves coordinate, dative, covalent bonds, where the ligand donates electron pairs to the metal. 5. Explains isomerism. Werner's theory can explain geometrical isomers, CIS strands, and optical isomers in complexes. 2. Limitations of Werner's theory. 1. No explanation of bonding mechanism. It could not explain how the electrons are shared between metal and ligands. 2. Cannot explain stability. Stability trends of complexes, like Ni, Co, were beyond Werner's theory. 3. Cannot explain magnetic and spectral properties. Paramagnetism, color, and UV visible spectra of complexes were not understood. 4. Does not predict reactivity. Reaction mechanisms of complexes were outside its scope. Example: Co-NH-Cl. Primary valency 3 Cl. Secondary valency 6 NH, forming an octahedral complex. Easy tip to remember: primary valency ionic, secondary valency ligands covalently, shapes matter, but bonding details are missing. Next important long question is: 3. What is effective atomic number? Calculate the EAN of the following: I, Ni, NH3, 6, 2 plus, 2, Fe, Cn, 6, 3, 3, Co, NH3, 6, Cl3, 4, Pd, NH3, 6, 4 plus. At no. Fe is equal to 26, Co is equal to 27, Ni is equal to 28 and Pd is equal to 46. Answer: effective atomic number, EAN, and calculation. 1. What is effective atomic number, EAN? The effective atomic number, EAN, is the total number of electrons around the central metal ion in a coordination complex. It includes: EAN is equal to the electrons of metal plus electrons donated by ligands. It is used to predict the stability of metal complexes. A complex is more stable if its EAN is equal to the next noble gas configuration, usually 18 electrons. This is called the 18-electron rule, similar to the octet rule in main group elements. 2. How to calculate EAN? EAN is equal to atomic number of metal, oxidation state of metal plus 2 times number of ligands times electrons donated per ligand. 3. Calculations. Ni NH superscript 2. Ni atomic number is equal to 28. Oxidation state is equal to plus 2d electrons is equal to 28 to 2 is equal to 26. NH is neutral, donates 2 electrons each times 6 is equal to 12. EAN is equal to 26 plus 12 equals 38. 2. Fe Cn superscript 3. Fe atomic number is equal to 26. Oxidation state is equal to plus 3d electrons is equal to 26 to 3 is equal to 23. Cn donates 2 electrons each times 6 is equal to 12. EAN is equal to 23 plus 12 equals 35. 3. Co-NH Cl. Co-atomic number is equal to 27. Oxidation state is equal to plus 3d electrons is equal to 27 to 3 is equal to 24. NH donates 2 electrons times 6 is equal to 12. EAN is equal to 24 plus 12 equals 36. 4. PD NH. PD atomic number is equal to 46. Oxidation state is equal to plus 4d electrons is equal to 46 to 4 is equal to 42. NH donates 2 electrons times 6 is equal to 12. EAN is equal to 42 plus 12 equals 54. 4. Importance of EAN. Complexes with EAN is equal to 18 for transition metals are usually very stable. Helps predict bonding, magnetism, and geometry of metal complexes. Easy tip to remember. EAN is equal to metal's leftover electrons plus ligand electrons. Closer to noble gas, more stable it is. Next important long question is: 4. List out the postulates of valence bond theory, VBT, of complexes. Discuss the VBT of the following complexes: Ni NH3 4 2 plus 2. Fe Cn 6 3. Answer: valence bond theory, VBT, and applications. 1. Postulates of valence bond theory, VBT. VBT explains the formation, shape, and magnetic properties of coordination complexes. Its main points are: 1. Central metal hybridization. The d, s, and p orbitals of the metal ion hybridase to form new equivalent orbitals for bonding with ligands. 2. Ligand donation. Ligands donate electron pairs to the empty hybrid orbitals of the metal ion, forming coordinate, dative covalent bonds. 3. Number of hybrid orbitals is equal to coordination number. The shape of the complex is determined by the type of hybridization. 4. Magnetic properties. Complexes are paramagnetic or diamagnetic depending on the number of unpaired electrons in metal d orbitals. 5. Type of complex can be high spin or low spin depending on the nature of ligands, weak strong field. 2. Application of VBT to complexes. Ni NH superscript 2. Ni superscript 2 3d 4s 4p. NH is a weak field ligand high spin, no pairing of 3d electrons. Hybridization, sp superscript 3, 4 orbitals for 4 ligands. Shape, tetrahedral. Magnetic property, paramagnetic, 2 unpaired electrons. 2. Fe Cn superscript 3. Fe superscript 3 3d 4s 4p. Cn is a strong field ligand causes pairing of 3d electrons, low spin. Hybridization, d superscript to sp superscript 3, using 2 inner d orbitals, 1s, 3p orbitals. Shape octahedral. Magnetic property diamagnetic, no unpaired electrons. 3 key points to remember. Weak field ligands high spin, usually tetrahedral. Strong field ligands low spin, usually octahedral. VBT cannot explain color intensities or spectral details, but it predicts geometry and magnetism well. Easy tip to remember. Hybridase metal orbitals, ligands donate electrons, shape depends on hybrid spin-style magnetic tails. Next important long question is 5. Define geometrical and optical isomerism and discuss them by taking following examples. Geometrical isomerism I MA4B2 2. MA3B3, optical isomerism I dot M A to B2 to dot M A 3. Answer: geometrical and optical isomerism in coordination complexes. 1. Geometrical isomerism. Geometrical isomerism occurs when the same ligands are attached to the metal ion in different spatial arrangements. Common in square planar and octahedral complexes. Ligands can be cis, together, or trans, opposite, in arrangement. Examples. I, MAB, octahedral. A is equal to one type of ligand, B is equal to another type. Cis isomer, the to-be ligands are adjacent same side. Trans isomer, the to-be ligands are opposite each other. Shape octahedral. 2. MAB, octahedral. 3 are ligands and 3 B ligands. Facial, FAC, isomer, the 3 identical ligands occupy one face of the octahedron. Meridional, MER, isomer, the 3 identical ligands are in a plane passing through the metal. These arrangements are geometrically different but have the same formula. 2. Optical isomerism. Optical isomerism occurs when a complex cannot be superimposed on its mirror image. These are called enantiomers. Common in octahedral complexes with bidentate ligands, like a ethylenediamine. Optical isomers rotate plane polarized light in opposite directions. Examples. I, M, A, B, octahedral. A is equal to bidentate ligand, B is equal to monodentate ligand. 2 possible enantiomers, delta and lambda. They are mirror images but cannot be superimposed. 2 M, A, octahedral. 3 bidentate ligands. Forms delta and lambda optical isomers. Each rotates plane polarized light differently. 3 easy tips to remember. Geometrical, same ligands, different positions, cis trans or FAC MER. Optical, mirror images that don't match light rotation. 4. Summary table. Isomerism example key feature shape. Geometrical, MAB, cis trans, FAC MER octahedral. Optical, MAB, non-superimposable mirror images octahedral. Memory trick. Cis trans is equal to positions, delta lambda is equal to mirror magic.